Hello guys, in this video tutorial I would like to explain calculating confidence interval. Uh, in this lecture, first I would like to give a brief overview that why we need confidence interval, and then I will give theoretically the procedure that what procedure we can follow to calculate confidence interval, and then I will do an example by using normal probability distribution. So let's move to the formal lecture. Okay, why we need confidence interval? You know that when we are calculating a single value, I mean that when we are estimating the population, let's we have suppose we have population, we have normal population with unknown mean mu, with unknown mean mu. Then we need to estimate this from sample data, and from sample data we can calculate x bar estimator of mu. So this is only a single value from a sample. So this may be equal or not equal, and most probably it's not equal. In very rare cases, this can be equal to the mean, the true mean of the population. Therefore, we need to have some range with some probabilistic range in which we believe with some confidence that the true value will lie in that range. Let me explain this graphically. Let's suppose this is mean mu, and then we estimate this by x1 bar like here, x2 bar here, x3 bar here, x4 bar, x5 bar. Suppose, okay, this is enough. You can do this. You can do far more, but I just want to explain this. So these are the point estimate for mu from different sample, and you can see that this value is closer and this value is really closer, the x bar 5. The other values are little away from, have deviation from the true parameter mu. So if you construct confidence interval for this, I mean like the upper limit something like this and the lower limit, these are not the exact value. You can do this exact value, but these are just, I'm just doing the approximation. So an limit for this and for on the other side here. Similarly, you can do limits for here, 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 and here as well. Then you can see that in most of these intervals, the true parameters mu lies. So this means that these are better estimated. I mean that these interval estimates are better. That with some confidence we can say that the true parameter lie in the range. So now I would like to explain what is mean by 95% confidence interval. This was one of the reasons that we need to calculate confidence interval, because a single value may not be equal to, and this is of course not equal because maybe in some rare cases that can be equal, because the population parameter mu is you can calculate for the entire population for all the units, and x bar you are calculating only for a portion of the data. So uh, I would like to explain 95% confidence interval here, and then we will move to the construction. 95% confidence interval. This means that if we draw 100 samples from population, from a population, and calculate confidence interval for each sample, then the 95 the interval of 95 samples, the interval of 95 samples may include the true value or the parameter mu. For 95%, of course, 5 may not include the parameter, but for the 95 sample out of 100 may include the true parameter. So this is the interpretation. Now the question is, we need to develop some procedure for calculating confidence interval, and of course this is theoretically not from some data. So what we need, there are various methods, maybe there are various methods, but we will use pivotal quantity method. Pivotal quantity method. For the construction of confidence interval. What is pivotal quantity? A pivotal quantity is a function that satisfies the following conditions. These conditions are: number one, we can write the pivotal quantity by Q. So the pivotal quantity, or you can say the pivotal quantity, is a function of sample observation, and parameters. Parameters. So we need to check this, the first one. Second one is the distribution of the pivotal quantity should be independent of the parameter. You can say unknown parameters. So these two we need to check these two conditions while going for calculating the confidence interval or any data. Now let's suppose we have a normal population problem. Suppose x1 up to xn is a random sample from normal population with unknown mean mu and known sigma square. There are two possibilities. One is sigma square is known and the other is sigma square unknown. So first we go for sigma square is known, for known sigma square. Okay, so this is, and now the question is construct 1 minus alpha 100 and to 1 minus alpha percent confidence interval for mu. So this is the question now. So what we need to do, to find the pivotal quantity. In this case, in normal case, you can think about the pivotal quantity. That's not difficult, because maybe you know that But remember the two conditions that pivotal quantity should be the function of the sample data and the parameters, and secondly, that pivotal quantity, the distribution of that pivotal quantity should be independent of the parameter. You can say unknown parameter. So for this case, the pivotal quantity, which we normally denote by Q, as just denote this by Q, that is equal to, you can say X bar minus mu divided by sigma divided by n square root. And remember that this is distributed normally with zero mean and unit variance. Remember that x, this is the standardized form of course, for x bar minus mean of x bar divided by standard deviation of the x bar. So you can see that this pivotal quantity is a function of the sample data, which is in x bar, of course, and the parameter mu. Sigma is known, so that is not to be considered as a parameter. That is okay, but as this is known already. So this is the function of the sample observation and the parameter. And secondly, the distribution of this pivotal quantity is independent of the parameter because the parameter is not involved here. This has normal distribution with zero mean and unit variance, standard normal distribution. So this is the pivotal quantity, and this is the one of the most important thing in the construction of confidence interval. Now, suppose 2 points Q1 and Q2 such that probability of Q1 and the pivotal quantity Q2 is equal to 1 minus alpha. And now, so these are the 2 points, the limits for which this is probability and the pivotal quantity. Now, Q1 and the pivotal quantity is x bar minus mu and square root. Q2 is equal to 1 minus alpha. You can see that now we can take, suppose, this quantity inside the brackets to find the limits. Now Q1 less than x bar minus mu sigma over n square root less than Q2. So now we need to find the values, the limits for the mu, because mu is unknown, remember. So we need to focus on this mu in this case now. So we need to do some manipulation, just multiply this here and then x bar. So this means that Q1 sigma square root less than x bar and Q2 sigma divided by n square root. Now you can subtract x bar from both sides. So this means that minus x bar plus Q1 sigma divided by n square root less than minus mu less than minus x bar plus Q2 sigma divided by n square root. Now you can multiply all each side by minus, so then the limits can be reversed. This will be the lower limit and this can be the upper limit because we are multiplying with the negative. This means that this is now the lower limit, x bar minus Q2 sigma divided by n less than mu less than x bar minus Q1 divided by n square root. So therefore the confidence interval or the limits, the confidence interval as lower limit minus and upper limit. Now the question is, How we can calculate? Because these are the two limits, and there may be many pairs of Q1 and Q2. I will write the statement again. Q1, the pivotal quantity Q2 is equal to 1 minus alpha. Now, if you look, these are these points Q2, Q1. So there may be many Q1 and Q2 which will satisfy this condition. But we need to search for those Q1 and Q2 which give the shortest confidence interval. Why we are interested in the shortest confidence interval? This, the precision is high for the shortest confidence interval. When the precision, the interval estimation has shortest length, then there are the precise confidence interval. Therefore, we need to find the shortest confidence interval, and for that we need to do some steps now, because there may be many Q1 and Q2 which satisfy this equation. So let's when the confidence interval these will be the shortest, we need to calculate the length of this interval, and if the length is shortest, this means that these confidence interval or the shortest confidence interval. The length L of the confidence interval as L equal to upper limit sigma divided by n minus lower limit minus x bar plus q2 sigma divided by n. So now you can write this first. You can take sigma divided by n square root common, q2 minus q1. So this is the length now. Now you can see that if the length is minimum, this is shortest, then the confidence interval are also shortest. So we need to do this. We need to make this shortest. To minimize, we can do the derivative. And remember that we need to take the derivative of this function with respect to q1 and treating q2 as a function of q1. To minimize L take the partial derivative of L with respect to q1 and treat q2 as a function of q1. So then this is equal to sigma divided by n, and partial derivative of q2 with respect to q1 minus 1, which is equal to 0. This means that partial derivative with respect to of q2 with respect to q1 is equal to 1. So this is equation 1 in this case. Now we know that probability of q1, this statement is mentioned above, is equal to 1 minus alpha. This means that we can write this cumulative distribution function of q2 minus is equal to 1 minus alpha. This is the property of the cumulative distribution function, that suppose x is a random variable and we write this like a b. We can write this cumulative distribution function at point b minus cumulative distribution function at point a. This is a property of the cumulative distribution function. Now again, take derivative of the above expression with respect to Q1 and treat Q2 as a function Q1. So in that case, you can do like, now I am just taking the derivative of this. So remember that cumulative distribution function is in the integration of the distributive density function. So when you are going reverse, this will again become the distribution for density function of Q2, and again taking the derivative of Q2 with respect to Q1, because Q2 is a function of, remember, function of Q1 minus f of Q1 n to 1 is equal to 0. Remember that derivative with respect to of, suppose, x, f of x, that is equal to density function of the x. So now you can do like this. On f of Q2 is equal to f of Q1. This means that partial derivative with respect to Q2 of Q2 with respect to Q1, that is equal to f of Q1 divided by f of Q2. Now you remember from equation 1 that this quantity is equal to 1. This means that Q2 is equal to 1. This means that because Q2 equal to 1 from equation 1, above. This means that f of Q1 is equal to f of Q2, and this further means that Q1 is equal to plus minus Q2, but Q1 equal to Q2 is not possible, because the probability of Q1 is equal to 1 minus alpha. If this is the same point like Q1 equal to 2, then this probability is not like this. So because of this, we say that Q1 is not equal to Q2. So this means that therefore Q1 is equal to minus Q2. So these are the 2 points which we needed to calculate. Now, in case of normal distribution, in case of normal distribution, suppose Q2 equal to Z alpha by 2, then Q1 equal to minus Z alpha by 2. And remember that the confidence interval which we calculated, they are, that is, that's look like lower confidence and lower limit is equal to, that was x bar minus Q2 sigma divided by n, and upper limit, that was x bar minus Q1 sigma divided by n. Now put Q1 and Q2 in these values, in this expression. The lower limit will become x bar minus Z alpha by 2 sigma divided by n, and the upper limit is equal to x bar minus into minus z alpha by 2 divided by n, which is equal to x bar plus z alpha by 2 divided by n. Therefore, the limits, therefore, therefore, the 101 minus alpha percent confidence intervals for mu as lower limit x bar minus z alpha by 2 sigma divided by n and x bar plus z alpha by 2 sigma divided by n. So these are the two limits which you can say 101 minus alpha percent confidence interval for mu when sigma is known. Now if now f if alpha is equal to 0.05, this means that 1 minus alpha is equal to 0.95. In that case, you can see the values from normal table, that is z 0.05 divided by 2, which is equal to z 0.025, and we can see the value for this against this probability, that can be 1.96. You can see the table. So therefore, the 95%, now you can say 95% confidence interval for mu when sigma is known as x bar minus 1.96 and to x bar plus 1.96 sigma divided by n. So this is the confidence interval, and these are the limits for mu when sigma is known, sigma square is known, and you need only now sample data to put in these expression and calculate the final value. These are the estimator. This is the lower estimator for the lower limit. This is the estimator for the upper limit. And now you need only sample data. We assume sigma is known. We need sample data, and this is x bar is this is based on sample data, and is the number of observation. And then you can calculate the final limits. So thank you very much for watching, and I will do in the next video for when sigma square is unknown, and then I will do large sample confidence interval. Thank you very much for watching. If you like the content, please subscribe the channel, and see you in the next video. Ciao.